Well, some go this way and some go that way. But as for me, myself personally, I prefer the shortcut, said by Lewis Carroll. You probably think that a qubit can be 0 and a 1 at the same time, or that quantum computing takes advantage of the strange ability of subatomic particles to exist in more than one state at any time. I can hardly fault you for that. After all, we expect places like the New York Times, Nature, Science, New Scientist, Time Magazine, and Scientific American, among many others, to be fairly reputable sources, right? Apparently not. Nearly every popular account of quantum computing has this 0 and 1 at the same time metaphor. Metaphor because it is certainly not literally true that the things involved in quantum computing are 0 and 1 at the same time. Remember that computers don't actually hold zeros and ones in their memory. Those labels are just for our convenience. Each bit of a digital computer is a physical thing that exists in two easily distinguishable states. Since we use them to perform logic, we could also have labeled them true and false. Now it should be obvious, true and false at the same time is just nonsense. It is a very misleading analogy. But what's the truth behind the metaphor? When we say a qubit can be in superposition, it means it can exist in a complex combination of states that we describe mathematically. Think of it as a spectrum of probabilities, where the qubit has different likelihoods of being measured as a 0 or a 1. It's not that it is both at the same time, but rather it has the potential to be either. As we delve deeper into the quantum world, it's clear that we're standing on the precipice of a technological revolution. However, with great advancements come significant challenges. Quantum computing is still in its infancy, and there are numerous hurdles to overcome before it becomes a mainstream technology. One of the primary challenges is error correction. Quantum systems are incredibly delicate and susceptible to environmental disturbances, which can lead to errors in computation. Another significant hurdle is scalability. Building a quantum computer that can outperform classical computers requires an immense number of qubits, and maintaining their coherence is a daunting task. Current quantum processors operate with a limited number of qubits, and scaling them up while ensuring stability is a monumental engineering challenge. Moreover, the field of quantum computing demands a new breed of expertise. Governments and private enterprises worldwide are investing heavily in quantum research and development. Let's move on to an equally crucial aspect: decoding quantum information. To extract information from this qubit, we perform a measurement. This is where quantum mechanics shows its probabilistic nature. Upon measurement, the qubit will collapse to one of its basis states, either 0 or 1, with certain probabilities. These probabilities are determined by the coefficients of the superposition. In the case of positive qubit, the probabilities are equal, meaning there's a 50% chance the measurement will yield 0 qubit, and a 50% chance it will yield 1 qubit. But how do we make sense of this in practical terms? Let's take an example from quantum cryptography, where qubits are used to encode and transmit secure information. When the recipient measures the qubits, they decode the message by interpreting the results of these measurements. The process ensures that any eavesdropping attempts can be detected thanks to the peculiarities of quantum mechanics. In quantum computing algorithms, decoding is about interpreting the measurement results to solve complex problems. For instance, in Shor's algorithm for factoring large numbers, the final step involves measuring the qubits to obtain the answer. The superposition and entanglement of qubits during the computation allow the algorithm to process many possibilities simultaneously, but it's the measurement that provides the final usable output. In classical computing, measurement is straightforward. You can read the state of a bit without altering it. However, in the quantum world, things aren't so simple. Imagine an atom encoding a qubit of information in its energy state. When you measure this qubit, you force the atom to release its energy as a photon if it's in a high-energy state. As a result, the atom collapses into a low-energy state. This collapse means that the physical system no longer encodes the quantum data, a process often described with verbs like destroyed, deleted, or collapsed. This brings us to a vital point. Quantum measurement is invasive by nature. To measure a qubit is to alter the system irreversibly. This isn't just a technical challenge, it's a philosophical leap. Scientists and philosophers still debate why reading qubits works this way. But let's simplify the concept. Consider measuring tire pressure. The air inside the tire has a fixed pressure whether you measure it or not. However, to measure it, you must let some air out, thus changing the very value you're attempting to measure. The more you learn about the system, the more you change it. Quantum physics takes this idea to the extreme. You can manipulate quantum objects without disturbing them, but you gain no information. Extracting the most information necessitates maximum disruption. But now let's delve into one of the most mind-bending phenomena in quantum mechanics called quantum entanglement. Imagine two particles that are so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. This is entanglement, famously dubbed spooky action at a distance by Albert Einstein. In classical physics, this seems impossible, but in the quantum realm, it's a fundamental aspect of reality. To understand entanglement, let's consider a pair of entangled qubits. When these qubits are created, they share a single, unified state. Measuring one qubit instantly determines the state of the other, even if they are light years apart. This instantaneous connection defies our classical understanding of space and time. Entanglement has profound implications for quantum computing and cryptography. In quantum computing, entangled qubits can perform complex calculations at unprecedented speeds by exploiting their interconnected states. In quantum cryptography, entanglement ensures secure communication channels, as any attempt to eavesdrop on the entangled particles will instantly disrupt their state, revealing the intrusion. But how does this spooky connection work? The key lies in the fact that entanglement is a purely quantum phenomenon. In classical physics, objects are independent and their properties are well defined. In the quantum world, particles exist in a superposition of states until measured, and entanglement links these superpositions across space. If quantum computing is based on such uncertainties, how can it be useful? Quantum algorithms are designed around the uncertainties associated with reading qubits. The task of an algorithm designer is to amplify the probabilities associated with correct solutions and minimize the probabilities of incorrect ones. So even if individual qubit measurements are uncertain, quantum algorithms as a whole guide the computation toward a useful outcome. For instance, consider the famous Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. It cleverly exploits quantum superposition and entanglement to sift through possible solutions more efficiently. Or Grover's algorithm, which provides a quadratic speedup for unstructured search problems. To summarize, a qubit is not 0 and 1 at the same time, but rather is described by a pair of numbers representing its state. Writing and reading qubits involve encoding them into and decoding them from physical systems, but with significant differences compared to classical bits. Most notably, reading a qubit is a random event that yields classical information and destroys the quantum information. The qubit state influences the outcome's probability, but isn't fully revealed in the process. So it's not clear whether we will see the quantum computer during our life. I wish we could see